We're continuing on, I think it's chapter 19, I think it is, with nuclear chemistry. So again, on tap today, we've got a couple things happening. Obviously, we're going to lecture. After lecture, we'll have our quiz at the start of lab time. And then after the quiz, we will then take care of experiment 11 for lab. So that's sort of what's on. I'm sorry, somebody had a question?
Yeah, what time do we submit our lab 10?
Now, lab 10 and lab 11 will be together. So the box for both of them will open up, probably towards the end of lab, like normal. Stuff
Thank
like
you.
that. Yeah. Since they're kind of, again, as we talked about the other day, sort of related to each other. So just going to turn them in together. Other questions on that? Okay. Let's do that. Let's get that out of my way here. Okay, so we started talking about nuclear chemistry here in this chapter, obviously. And nuclear chemistry, again, is a little bit obviously different than, excuse me, than sort of chemical reactions, especially nuclear reactions are very, very different than chemical reactions. So as we talked about last time, when we're dealing with chemical reactions, normal chemical sort of equations and things happening like that, we're really dealing with electrons and electrons really being involved in those reactions. And that's really why in those type of reactions, we have that conservation of really the elements there. We start with a certain number of, say, oxygens, we'll end with a certain number of oxygens. And that's only because we are basically changing the electrons. And if you remember, really out of protons, electrons, and neutrons, the thing that's really important in terms of what element we're dealing with is actually the number of protons. So in normal chemical reactions, it's just electrons, nothing gets touched in terms of protons or anything like that. So we do have that sort of conservation of the elements in a chemical reaction. That is very different in a nuclear reaction. In a nuclear reaction, we actually do, and pretty much most everything that's happening is sort of happening inside the nucleus. So obviously, if we're doing things inside the nucleus, maybe protons become neutrons, neutrons become protons, and so forth. We're changing the number of protons a lot of times in these reactions, and we really end up with really no sort of conservation, if you will, of elements. So what we start with and what we end up with in terms of the elements are really, quite different. And that's really revolving around what's sometimes referred to in nuclear chemistry, the nucleons, which is basically the particles inside the nucleus, the protons and the neutrons. So as we change the protons in these reactions, we're changing the elements. And that's why when we talked about, for example, balancing nuclear equations, we do it slightly different than how we balance a chemical reaction. In a chemical reaction, we balance everybody by their coefficients. In a nuclear reaction, we basically want to make sure, as we saw, that when we look on the left-hand side of the arrow, all the mass numbers equal each other. And the right-hand side of the arrow, we basically have the same total number of mass numbers on the left and right. And same thing with the atomic numbers, which is on the bottom. We want to make sure when we add up everybody's atomic number on the left-hand side, it equals pretty much everybody's atomic number there on the right-hand side. And that will essentially balance our nuclear equation. The thing that you really want to look at is sort of like the missing atomic number. So remember that every element has its own atomic number, and that, along with the periodic table, obviously would be very helpful in determining sort of what is the missing sort of element in a nuclear reaction. You also obviously could add up the top numbers there to figure out the missing mass number. Remember as well, we do see some different sort of symbols along the way here. We have alpha particles, which is, either symbolized with the alpha symbol or sort of the helium symbol. So, alpha particles, oftentimes represented like that, are obviously with the alpha symbol. We also have beta particles, which again, we'll use sort of the beta symbol or an electron sort of symbol here. We also have things like protons, which, we'll use sort of these symbols. Um, so there's a lot of other sort of symbols that we saw along the way. We also saw neutrons. So neutron, will have sort of that symbol. There's also a positron, which will basically have a plus sort of symbol. And again, we'll use the same sort of symbols as our beta particle. So knowing these guys as well is really important, especially the mass number, atomic number that happens with each of those, because that will definitely help you be able to balance out your equations. Now, in addition to that, we also started talking about really at the end there, sort of stability. And there's a number of different ways you could kind of look at stability. And one sort of important way is what is sometimes referred to as the N to Z ratio. And that's sort of your neutron to proton ratio that you find. And when you do that, there's a certain sort of ratio area that's referred to as the belt of stability, the valley of stability. And within that sort of area, you have pretty much sort of stable uh, nuclides and isotopes in that case. It does vary depending on sort of the atomic numbers. So if the atomic number is somewhere between 1 through 20, an acceptable sort of stable ratio is believed to be about 1. If you got 20 to 40, 1.25 is sort of the acceptable ratio. And if you're kind of 40 to 80, then you're moving into like a 1.5 in terms of the ratio. There's also some gray areas in there, as we talked about. Again, if you're kind of moving from like that 20th area to 21 in that sort of area, as one stops and one starts in terms of the atomic number. Some people will say if it's between 1 and 1.25, it's still going to be stable. So again, as we talked about, not really the official rule, but we'll use it for our class here. Again, we'll use those cutoff as really like hard cutoffs. So either it really is sort of that number and it's stable, or it's too high or too low if it's not that number. But again, sort of in real life, there is sort of like a little grayish area in between those cutoffs that sometimes people will again say it's sort of stable still. Now, if the ratio, for example, is too high, what ends up happening is that guy will then go through a beta decay. And what that's going to do is basically try to bring it, if it's too high, kind of bring it back down towards that belt of stability or the valley of stability. And the opposite sort of will happen if we sort of have a too low ratio. We'll end up with either a positron emission or an electron capture. And what that's going to do is essentially kind of bring it back up towards that valley of stability. Again, as we saw, it may not perfectly get you to a perfect ratio by doing any of those things, either the beta decay, positron emission, or electron capture, but it definitely should move you closer to that valley of stability as well. Also, a reminder, as we saw, that there really is no difference in terms of sort of the outcome for our too low sort of ratio. And that's why we can do either a positron emission or electron capture. They both pretty much will yield the exact same guy at the end. So that's why, again, you do have that sort of couple of options there. We finished up talking about the idea of some other ways to look at stability. And in addition to the N to Z ratio, really the other sort of major thing that people sort of look at is sort of, is it even in terms of neutrons, protons, odd. And again, as you can see on that table that we discussed, pretty much if you have like even number of protons, even number of neutrons, that's sort of your best situation in terms of stability, it turns out. And as you can see, there's like 157 of them that are pretty much stable in that arrangement. You can see it dramatically drops when we get odd protons and odd neutrons. There's only about 5 that are sort of stable in that arrangement. And again, it's just been found to be a little bit more stable. So even is another sort of important thing to look at in terms of stability. Any questions on any of that stuff we talked about last time? Okay, so then the next thing we're going to talk about is a decay series. And a decay series is pretty much what it kind of sounds like. It is, we start with really a unstable sort of nuclei. It's going to go through a decay process, and it will continue to basically decay until it hits, something that's sort of stable. And this sort of one decay process after another is what is referred to as a decay series. Again, what we start with is sort of the parent, and the daughter nuclei is sort of what is formed as a result of that. Now, there's a couple different ways you could kind of determine, in a, say, decay series, what you would end up with. sort of at the end. And we'll talk about a couple ways to do that. But first off, one sort of mathematical way you could kind of do it, if you're really just interested in not what you form at every sort of step along the way in the process, but sort of this is where I'm starting, what am I going to get at the end? You can basically count the number of alpha and beta decays that there are in this series. And what you could do is from the mass number, basically subtract 4 for every alpha decay. So for every alpha decay, from the mass number, which is our number up there on top, we would subtract 4. And for every alpha decay, we would subtract 2 from our atomic number. And for every beta decay, we would actually add 1. So for every beta decay, we would add 1 to our atomic number. So for example, if we said we were starting with, say, uranium 238, and again, we could get the atomic number there from the periodic table, which is 92. And let's just say that this guy went through a decay process of alpha, I'm just making this up, beta, we'll just do that move right there. So the couple of different ways that you can really approach this type of problem is to essentially do nuclear equations like we did earlier, sort of step by step, and it's a good way to do it. You probably won't screw up too much if you kind of do it that way. So one approach would be just to do some equations like we did earlier, balancing them. Start with our uranium 92 is going to first go through an alpha decay. And again, just like we did before, we would find our missing atomic number, which in this case would be 90. And our missing mass number, which would be 234. And again, go into periodic table, we see number 90 is TH. That would take care of that decay process. What would happen in this case is then this guy would be what we would start with, 23490 TH. And then that guy would then go through a alpha decay. And again, we would do the exact same thing here. So it looks like perhaps 80, what we got there, 88, I think, and a 230 up on top. So again, if we go to the periodic table and we find number 88, it is Ra. And that would take care of the second step. Then that guy that we just produced would go through the next process. If I write the number right, there you go, 230, 88. And in this case, he's going to go through a beta decay, which is 0 minus 1 E, our beta symbol. Here with the negative 1 on the bottom means actually it has to go to 89 to get me to the right spot there. And 89 would be AC. And that would take care of our beta emission. And lastly here, that 230, 89 would go through a beta decay. Again, you can use the beta symbol if you want, or you can use the E. Same thing here. We're going to have to increase by 1 here, and that's going to get us to 90 to 30, and that puts us back to TH. So along the way, the nice thing about sort of doing it this way is you probably won't screw anything up, but you also can sort of get the products that are made there in each of these steps. If you were really just interested in knowing what you get at the end of the process, you could follow the math part of it. So if we kind of did the math part here, 238.92, we have 2 alpha particles. So we have 2 alpha decays. That means that we subtract from the top number -4 and -4, also from the bottom number -2 and -2. And we have 2 betas, which means to the atomic number, we should add 2 back. So if we just do that math really quick, that is 238 minus 4 is 230 up on top. That's 92 minus 2, which is 90. Minus 2 is 88. Plus 2 brings us back to 90. And you can see there, mathematically, we get ourselves to the right answer at the end. But again, if you want sort of a step-by-step and what happens step-by-step, maybe doing it this way is good. You also could just do it mathematically and figure out step-by-step if you want as well. Any questions on that sort of process there? And again, obviously I just made this up, but in a normal situation, these guys would continue really to go through this process until they really hit something that's sort of stable for them. Obviously, it would be probably a lot more decays that happen here than is these four. So for uranium, for example, here's an actual sort of picture of that. And actually what happens is there's a couple of processes that sometimes happens along the way. But again, we see our uranium 238 up here. And eventually it will continue down no matter which path it sort of takes at this point as it diverges one way or the other, as you can kind of see here. It eventually all ends up down here to basically lead 206, which is a stable situation for it. Any questions on that there? Okay, the next thing we're going to then talk about is kinetics and radioactive decay. So all radioactive decay follows what is referred to as first order kinetics. Kinetics really is the study of like how fast something occurs, a reaction. How fast, or I guess slow, a reaction occurs. We're going to talk officially about kinetics at the end of the semester. We do it here at the very last chapter, which is actually going backwards in chapters, but we talk officially about kinetics at the end. So when we're talking about sort of kinetics of radioactive decay, again, it does follow that first order kinetics. And there's a couple of important sort of equations that are used for that. And this is one equation, which is sort of nuclear chemistry sized, if you will. In normal first order kinetics, there's basically a time and concentration equation, sometimes referred to as an integrated rate law, and it is the natural log of A is equal to the natural log of A naught minus KT. And this is sort of your final concentration. This is your initial concentration. This is what is referred to as the rate constant. And it is different K. It is actually, I'll do it like this. That is lowercase k. That's actually the rate constant. Not to be confused with everything we've been talking about, which is, for dramatic purposes there, the big capital K, which is the equilibrium constant. Yeah. So here with kinetics, we deal with the rate constant, kind of tells us how fast the reaction is happening. T here also is actually time, not temperature. So this is time and not temperature. Now, there's a half-life equation that goes with it, and it's right here. You'll sometimes also see it, the half-life of a first-order reaction is the natural log of 2 divided by the rate constant. If you take the natural log of 2, that gives you 0.693. So that's where that number comes from. Half-life is pretty much what it sounds, right? It's half the time, or sorry, it's the time it takes for half of what you started with, basically to disappear. So if you started with 10 after the first half-life, you have 5. After the second half-life, you have 2.5. And after that, you need a calculator, but you keep dividing by 2, basically. And, about 10 half-lives, pretty much everything will be sort of gone. Now, sometimes in nuclear chemistry, which is what we see here, they'll change out some of the symbols, and they'll use something like the natural log of n is equal to the natural log of n naught minus, and they'll actually use lambda sometimes nt. And these are the same things. This is sort of your final. And a lot of times, though, in sort of nuclear chemistry, we're not dealing with concentrations like we are in regular chemical reactions. So a lot of times we deal with things like grams, milligrams. It doesn't actually have to be a concentration like molarity when we use this equation. It could actually be things like radioactive counts and stuff like that. This is, again, kind of our initial, all those things, either, grams, milligrams, could be concentration, I guess, very rarely in nuclear chemistry, some type of radioactive count or something like that. Again, sometimes you actually use lambda to represent really the rate constant, but is sometimes in nuclear chemistry referred to as the decay constant. So again, they like to have their own words sometimes in nuclear chemistry, but it's really the same thing as the rate constant, but they'll sometimes call it the decay constant here. And T again is, like I said, time. This, you might be wondering why it looks a little, maybe a little different here. That's the mathematical relationship, right? So, if you take the natural log of n minus the natural log of n naught, that is basically that relationship. That's sort of like a math relationship there. And as I mentioned before, sometimes we can use rates instead of rates of really radioactive decay instead of concentrations or something like that. Personally, I kind of just roll with the normal sort of kinetics version of these equations. So again, when I do these examples, you'll probably see me write it like this, but it really is sort of the same sort of equation as this guy. And it all works out the same. So, if you see me kind of just go with these equations, it's really the same thing. So when we talk about sort of first order kinetics, there's two sort of graphs that we commonly see associated with first order kinetics. One is the concentration versus time. And as we would expect, what we see is early on in terms of time, we have a lot. And as time goes on, we're gradually, obviously, decreasing the amount of our nuclide as it is going through, obviously, decay, which means fancy word of saying it's getting smaller, right? It's basically deteriorating, it's decomposing, if you want to kind of think about it that way. Here again is our integrated rate law. And again, you can see they will sometimes kind of insert those kind of nuclear chemistry sort of symbols in place of our normal kinetic symbols. But one thing that we typically see, regardless of sort of what we're dealing with in terms of either nuclear chemistry or regular chemical kinetics, is if we take the integrated rate law and we actually rearrange it into minus kT plus the natural log of A. This is the integrated rate law written in the form of a straight line. And that is y is equal to mx plus b. And as you can see, that relationship here does yield us a straight line. On the y, we plot the natural log of a or n. On the x, we plot time. And that again yields us a straight line. It yields us a straight line where the slope is equal to minus k. And this line is a negative slope. Yeah. And that negative and negative will give us a positive decay constant, I guess we'll call it in this case, our rate constant in this particular case. So this is really, this graph here is really the graph that's mainly associated with first order kinetics. When we talk about kinetics, we'll see this graph again. We'll actually see a linear version of that graph, which is actually for zero order reactions, but all first order kinetics happens for radioactive decay. And in addition, the rate equation here and the half-life equation, you do need to, in a lot of cases, kind of use these guys together. So in a lot of cases, you'll be given some information. Maybe they want you to find this guy and they give you this piece of information. They give you the time, but they don't give you the decay constant or the rate constant, but they will give you the half-life. So a lot of times you'll have to kind of use both of those equations sort of together. And in most cases, you're going to use the half-life equation to figure out the decay constant, and then use sort of the integrated rate law there to figure out, what it's asking, maybe it's the time, maybe it's how much is left and stuff like that. Any questions on that? Also, and again, not super important maybe for this because, again, radioactive decay always follows first order. But one way you know that you are dealing with a first order sort of reaction, especially when you're dealing with kinetics, is to look at K, which is the decay constant or the rate constant. And the units associated with it are always 1/seconds or reciprocal seconds. It's some type of unit of time, doesn't necessarily always has to be seconds, but it's 1 over some unit of time. Seconds is most common because most of the time when we do reactions, in experiments, we don't sit there for days and days doing them. So, they usually happen relatively quickly. And that's why time in terms of, units, seconds are very common, but it can be something like 1/minutes, 1/days, 1/years. And all that tells you it is a first order type of reaction. Any questions on that there? And in terms of those units, it's super important as well. And this part of the sort of formula that they are in the same units, because sometimes you may be given the time in like days, and you may be given, the rate constant in minutes or something like that. So you want to make sure you're in the same units, especially when you're using that. Here are some half-lives of some nuclides, and you can see, sometimes the half-life is a very, very long time. That's 1.4 times 10 to the 10. I don't think any of us will be here for one half-life to occur for that, or even uranium-238. It's a very, very long time for the half-life to occur. Obviously, we will not be here for that either. And these are the sort of decay methods on some of these things. This is carbon, which is 5730 years. But some things are super fast. Obviously, this guy, every basically minute, it's losing half of what it started with. So that is very, very fast. And including here as well. That's very, very fast in terms of that. So sometimes things have very long half-lives. Sometimes things have very short half-lives. Some things in between sort of half-lives. It does depend maybe, on your application as to maybe what you would want to use, as we'll talk about a little later on in this chapter. Clearly, if you use any of this stuff for, say, medicine purposes, you wouldn't want to probably choose something with a very, very long half-life. You probably would want something with a kind of short half-life and stuff like that. So let's take a look at one here. Why don't you give it a try here? We have, excuse me. We have, what we got here? We got 1.35 milligram sample plutonium-236. We want to know how much mass will remain after 5 years, and the half-life of plutonium is 2.86 years, I believe. So why don't you take a second and see what you come up with? And what we're looking for is basically how much should remain after that period of time. So take a minute or two, and then we'll talk about it. Okay, look here. And see how we're doing. So again, as soon as you see sort of something about concentration, something about time and what's going to be left or how long it takes, is going to be a kinetics type problem. And again, the good thing about sort of radioactive decay is it's going to always be first order, which again means we pretty much have our formulas here that we should be using. And we got both of those. So in this particular case, you have 1.35 milligrams. So that is like your initial starting amount there. We are going for 5 years, which is our time. And we want to know how much is pretty much left over. So we're looking for this guy. We have this one given to us. We have this given to us. So very much in these type of problems, we're sort of missing our decay constant in this case to allow us to properly, obviously, determine how much is left over. But the one piece of information they did give us as well is the half-life. So that we can use as well. So we could use that to figure out our decay constant by rearranging this. And that would be the natural log of 2 divided by the half-life, which means the natural log of 2 divided by 2.86 years. And that gets us natural log of 2 divided by 2.86. Looks like something like 0.2424, we'll call it. The units here are basically 1/years is the units that we got going on here, are reciprocal years.
Professor,
that means, yeah.
Why is it ln2?
That's the formula for the half-life for a first order reaction. And so it's always the natural log of 2 over K. Natural log of 2, when you do it on your calculator, is that 0.693 number. So if you just
okay, understood.
Yeah, so if you just take that natural log of 2, that's basically what it is, 0.693. Other questions on that? Okay, so pretty much at this point, we just got to kind of plug stuff in. So we're going to be looking for this guy. And then we'll see the natural log of our initial, which is 1.35. We're going to subtract it from our decay constant there that we calculated. And what I'm going to do is just get that out of the way there. So I got a little bit of room. And then we obviously have our time. And this is what I was talking about earlier as well. In this particular case, we have years and years, so everything's good here, but it is very, very common that these two guys will have different sort of units of time. So you want to make sure you always kind of check that to make sure that's, not the case, that they're different or anything like that. If we kind of clean up everything there on the right-hand side, we're going to take basically the natural log of 1.35, and I guess it would help to punch it in, right? 1.35. We're then going to subtract it from 0.2424 times 5. And if we do all that, we end up with minus 0.911895. To get rid of the natural log, we're going to do the E of both sides there. And obviously, when we do the E of both sides, those guys cancel. We end up with A. And then obviously we take the E of that along with obviously its sign there. That's negative. And it looks like we end up with 0.402. The units of this guy will be the same as the original there, which would be milligrams. And that would be how much would be left over when we're all said and done after 5 years. Any questions on that calculation there? Now, we could also make sure it does make sense, right? So we started at 1.35. This is something that is going through radioactive decay, which means if you remember sort of our graph, it should be decreasing with time, right? So obviously what we ended up with is less than what we started with, which means we probably hopefully didn't make a mistake anywhere along the way. Any questions on that there?
Professor?
Yeah.
How many decimals should you have when you calculate K? Because I only had 2 decimals and I got a pretty different number than you.
Yeah, so in this case, if we just kind of look at maybe the numbers, every number we have is kind of 3 sig figs, right? So, like normal sort of calculations, you might not want to round too much along the way until you kind of get to the end, which is why we kind of cleaned it up probably to 3 sig figs here. And again, for example, on my calculator, you could have just went with the whole number, but I at least took it further than probably 3 on that particular one, just to be safe. So try not to round too much along the way until, maybe the end and stuff like that.
Okay.
Because you definitely will, as you probably notice, especially when you start doing this type of stuff, the slight rounding might not seem like a big deal, but it gets sort of amplified a lot when you kind of do those type of calculations involving things like natural logs, the inverse of natural logs, and things like that. Other question? Okay. Other questions? Okay. So yeah.
Oh, sorry. I just had a quick question. How would you put for the ln squared over 2.86? How would you put that in the calculator to get that?
So personally, what I do is, again, the natural log does equal this number. So if you want, you could just punch that number in. But if you're going to do it, you just actually hit the natural log button and 2. If you have a display calculator, if you don't have a display calculator, then you got to hit 2 and then the natural log button. Or if you have a display calculator, natural log button, then 2, and then hit equals, and then it should spit out pretty much this number, and then just divide it by, whatever it was there, 2.86. Other questions on that? Okay, let's try another one so we could test our calculators and all that good stuff here and see how we do. All right, so give this one a go. We got Radon 222. It's produced, and if there's 10.24 grams of it in the house today, how much will be there in 5.4 weeks if the half-life is 3.8 days? So take a couple minutes there and see what you come up with. Okay, so let's take a look at this one here, kind of approach it the same way. Let's just see what was given to us. Obviously, we know we're going to go with our kind of standard formulas here for radioactive decay, which again are going to be these two here. And in terms of what was given to us, looks like we have our initial here, which is 10.24 grams. We want to know, how much is going to be there after 5.4 weeks. And so, and that is our initial there. And that means, again, if we just kind of check off things, or we're looking for that, this is what we have. We're again missing our decay constant, but we are given the half-life here, which is 3.8 days. Now, as I was talking about before, obviously we're going to solve for K just like we did previously here. And that K is going to go into here with our time. So again, you want to look at units here. We do have weeks in terms of the time. We do have days in terms of the half-life. So again, these are different units here. So at some point along the way, you do need to do a conversion to get them into the same units. Otherwise, things will not cancel out sort of correctly. So what I'm going to do, I think, is we will do... I will convert my days into weeks. Why not? So we got 3.8 days. And there are, I think, still 7 days, or 5, I guess, or 2, or whatever your work week is, I suppose. 7 days in a week here we will go with. And the days will cancel. And that will get us 3.8 divided by 7. Looks like something like 0.54286. Again, here, I'm just going to take it out to a few digits and not round too much. And we got weeks. That means that we will put it into here. So that's going to give us the natural log of 2 is divided by 0.54286. And that would be our natural log of 2 divided by our number there. Going to give us something like a decay constant of 1.27. We'll go 7. And again, the units here are actually going to be 1 over weeks, or reciprocal weeks, as these guys are weeks here. Any questions on that so far? Again, you could have left it in days and converted this to days, and it would become out the same, in the grand scheme of things. That means that we have natural log of A is equal to the natural log of our initial, which was 10.24 grams. And then we're going to go minus our 1.277 1 over week times our 5.4 weeks. Again, this is why it's important. The weeks will cancel each other out. And again, if we kind of clean up the right-hand side in this case, we got a natural log of natural log of 10.24. And we're going to then subtract it from 1.277 times 5.4. That's going to give us the natural log of A is equal to minus 4.5695. Again, I'm going to do the same move, take the E of both sides there. And that's going to give us too many buttons to choose from there. That's going to give us basically an A that is equal to 0.01, we'll call it. And that it would be, which was grams. So we'll go with grams in this particular case as well. Any questions on that one? Again, depending on your rounding, depending on if you want maybe to days, you might end up with 0.011 or something like that. Again, it's okay. It's just some rounding or maybe where you rounded. Any questions on that particular one? Also, again, does make sense as, we started with 10.24. We obviously ended with a lot less. Any questions on that one there? Okay. So this is again a way we could figure out, how much is left over. We could also use it to figure out how much time and stuff like that. So let's talk a little bit about kind of using these kinetics equations here and radioactive decay to, figure out things like maybe how old something is through maybe radiocarbon dating, some type of radioactive type of dating. And we could do that. So for example, here, very badly done here. These arrows, I gotta fix them. We have something like radiocarbon dating up on top, and basically, just to rewrite this one, I think it's okay on your notes if I'm not mistaken. I hit something and moved all my arrows out of place. So again, basically we're using radiocarbon dating here to figure out, how old something is by looking at, how much carbon 12, for example, our carbon is left over at that particular case. Same thing here. This would be carbon 14 going through that decay process here. And stuff like that. We would use, if we were doing something with carbon, we would use the half-life here of carbon that we saw earlier, which was 5730 years for the half-life. Also do something like uranium dating here. And again, we can figure out how much lead is left over. And again, this equation looks something like this here. And obviously the half-life there for our uranium would be 451 times 10 to the 9 years, which is a long, long time. And really, we could figure out how much is left over. All of this lead would have came from the uranium, and using some calculations, we could really figure out sort of how much is left over. So let's take a look at one and kind of see sort of how we kind of incorporate this into our kinetics equations. So for example, let's say here we had a ancient skull that's giving 4.5 DIS-MnGc. So you may be thinking, what the heck does all that mean? So this is basically a unit of radioactive decay. This is disintegrations per minute. And this is actually not Celsius. This is actually per gram of carbon. So that is like per gram of carbon. And why would that be important? Well, that would be important because we are now talking about really carbon here. And we would want to use the half-life for carbon, which is our 57, excuse me, our 5730, which we just saw on that previous slide there. So sometimes people see the C and they automatically think Celsius here, but it is per gram of carbon. And again, that's why we would know we should probably be using carbons there, half-life. If a living organism has 15.3 disintegrations per minute per gram of carbon, how old is the skull? So essentially what we're doing here is our still first order kinetics. And in this particular case, we got a couple of things sort of given to us. We have the ancient skull, and that's pretty much the final, right? Kind of like when you're dead, you're final. And living means you're still going. So that's like your initial here. And obviously we're looking for how old is it. So we're actually looking for time in this particular case. So kind of like the previous one, we're actually missing still our decay constant to allow us to do that. And again, that is why knowing that this means per gram of carbon is important, because then we could go and get our proper half-life for carbon and obviously solve for our decay constant. So that would be sort of the first thing we'd want to do, kind of like what we did previously. Our decay constant would be the natural log of 2 divided by the half-life here. And that would be the natural log of 2 divided by 5730. Again, years are the units there. That's going to give us the natural log of 2 divided by 5730. And that's going to give us something like 1.209 times 10 to the minus 4 reciprocal years. All right. Oops, like that. Any questions on that one there? All right, so now that we have this, we actually can solve for t. So in this case, again, we're going to go with our natural log of 4.5. That's sort of our final rate, is equal to the natural log of our initial rate, which is a larger number. Again, this is radioactive decay, which means what we start with should be higher than sort of what we end with, right? So that's how we know, the 15, which is the larger numbers where we started with, and the 4.5, which is obviously the smaller number, is where we ended basically on this journey. This is going to then be minus our decay constant there, to -4, again, reciprocal years. And we're actually going to solve for t in this case. So I'm going to kind of clean up the left-hand side, and I'm also going to bring this guy over. So I'm going to subtract that guy over to the other side. So on my calculator, I'm not going to get fancy with it. I'm just going to simply go natural log of 4.5. I'm going to hit equals. I'm then going to subtract the natural log of 15.3. And that gives me minus 1.22378 is equal to minus 1.209 times 10 to the -4 reciprocal years times t. At this point, obviously, I'm just going to divide this to the other side, and remember that I'm also taking the negative with me, and that is 1.209 times 10 to the -4 on both sides. And if I do that, I end up with about what we got here, 10122. The units here would be years, would be our time, and probably should round it down there to something, maybe a few little less than that. So, we'll do something like 1.01 times 10, make it all fancy. 1, 2, 3, 4 years would be our time. And that's like 10,000 years old, pretty much. Yeah. Any questions on any of those steps there? So this demonstrates really nicely what I was talking about before. Again, sometimes you guys probably don't have that in your sort of head, but sometimes in this class at schools they actually do kinetics first and then they do this stuff. When we do kinetics first, we strictly deal with concentrations, pretty much molarity most of the time. But again, this demonstrates nicely. It doesn't necessarily have to be concentration. It can be. It could be molarity. It can be grams like we did previously. It could be milligrams, or it could be some type of unit of radioactive decay or rate of radioactive decay that you could kind of put into these guys. The key is just to know, basically, this is your starting point, your initial, and that's sort of your ending point there. And it's whatever the units may be is sort of the units that you end up with. Any questions on that particular one there? Okay, so why don't you give another one a go here just to see. So we have dated a civilization back to 15,600 years ago. If we have a living sample that gives 20 counts per minute per gram of carbon, what would be the number of counts per minute per gram of carbon of a piece of rice that was found on the site? So take a second there. And again, I'll give you a hint. Obviously, we're using carbon again. So if you need the half-life, you probably should be using the same one as we just did in the previous problem. So take a couple minutes and we'll talk about it. Okay, let's take a look here. So same approach. We're going to use our two equations here. All right, so in this case, they definitely give us time, which is 15,600 years. We have a living sample. So again, living would probably be initial there, which is 20 counts per minute per gram of carbon, basically. That was very scribbly bad there. What would be the number of counts? So we're looking at what it would be when it's all said and done there. And if we found a piece of rice there. So We are looking, actually, I did backwards there. There we go. We are looking for what we got left at the end. There we go. So we're looking for this guy. We are given this guy. We're given the time. Again, here we are not given the decay constant. Because it is grams of carbon, again, we could use the same half-life as we used on the previous one, which was 5730, I believe. And really it's going to give us the exact same sort of outcome in terms of our decay constant as what we got on the previous one. It'll be the natural log of 2 divided by our 5730. And that gets us something like 1.209 times 10 to the minus 4 reciprocal years as our answer there for our decay constant. At this point, we then have this. So we're going to natural log of A equals the natural log of our initial, which is 20. Minus our 1.209 times 10 to the minus 4 reciprocal years times our 15,600 years. Years will cancel each other out. We're going to kind of clean up everybody on the right. And if we do that, we end up with the natural log of 20 equals minus 1.209 to the minus 4 times 15,600. Going to give us a 1.10969. Again, we're going to E both sides there. That's going to give us a final here of 3.03, and at this point the units of this would be the same units that we have here, so these would be 3.03 basically counts per minute per gram of carbon. So it'll be something like that. Again, we do see that it decreased. It started at 20 in our initial. Again, as it's going through decay, is starting to decline. As we start losing and it decays, obviously they're not going to be giving off as much radioactivity as well as it goes through half-lives and so forth. Any questions on kinetics, how to figure out years, how much is left over, any of those things there? Okay, then the next thing we're going to really talk about is fission and sort of what happens with fission, where that energy comes from fission. Good talk. Let's go back. First off, fission essentially is the idea where we have really a unstable sort of nuclei, and this could happen spontaneously. This could happen by kind of shooting a particle at a stable guy and making it unstable. But ultimately what happens in a fission reaction is it goes through decay process, and it usually will create kind of two new nucleuses, what's called Y and Z. And it usually will create some neutrons, and it usually will create some energy in this process. Now, you know, do we always know the two that come out? The answer is no. And again, this spontaneously can occur. There's a good way to maybe predict, you know, what you might see, but, you know, it does typically split off into a couple of new nucleuses. Neutrons are sort of generated as well, and a lot of energy is generated. So one way we could kind of look at sort of the energy associated with this is through Einstein's equation, which is E is equal to mc squared. C obviously being our speed of light, which is our 3 times 10 to the 8 meters per second. M is mass, and we'll talk about sort of what that is in just a bit here as well. But as we talked about, you know, when we're dealing with sort of nuclear processes and stuff like that, we're really dealing with those guys in the nucleus. and it usually results in a lot of energy being produced. So, for example, uranium-235, if you take 1 mole of it, it produces something like 10 to the 13 joules of energy, as compared if you took like the most sort of exothermic reaction, chemical reaction, you're looking on the order of 10 to the 6 joules per mole. So a tremendously bigger or larger amount of energy is usually sort of developed here in these sort of nuclear reactions. So when these processes occur, and when, for example, a nucleus sort of occurs, there is sort of a difference between the mass of sort of the isotope, if you will, and the mass of like all the particles that sort of make up the nucleus. And that little bit of mass gets sort of converted into energy in this process. And that is what is sometimes referred to as the mass defect. So the mass defect is essentially sort of that energy difference that occurs as a result of really there's this slight mass difference between, say, the protons and neutrons that make up a nucleus and the actual mass of the isotope itself. And that little bit of difference is basically made up through, you could use Einstein's equation to do that. Or there's other ways you could kind of figure it out as well. And that energy that's released in this process when this occurs, when the nucleus occurs, is what's sometimes referred to as binding energy. And sometimes binding energy or nuclear binding energy is given in 2 common units. One is mega electron volts and one is joules. And there is a relationship here between a mega electron volt and a joule, and also an AMU, a mass defect. AMU is atomic mass unit, is equal to 931.5 mega electron volts. So if we look at something, for example, like, say, fluorine, let's take a look at fluorine 19, I think is what we got there, right? Yeah. So we'll look at fluorine 19 here. And again, if we go to periodic table, we got 9 in terms of the atomic number. And let's say the mass of this isotope here is 18.9984 AMU. So we can actually figure out, the energy that's sort of happening here when we sort of formed something like fluorine 19. And we could do it by first figuring out the number of protons, which obviously would be 9 in this case. The number of neutrons, which is the other part of the nucleus, would be 19 minus 9. Mass number minus atomic number gives us 10. And it is the difference between the mass of those 9 protons added to the mass of the 9 neutrons that will give us what is referred to as the mass defect. So if we were to calculate the mass defect, what we would do is we would take 9 for the protons, we would times it by the mass of a proton, which is 1.007825 AMU. We would then add it to our 10 neutrons that are there, times the mass of a neutron, which is 1.008665 AMU. And we would then subtract it from the atomic mass of the isotope, which is 18.9984 AMU. And if we do all that, we end up with 0.1587 AMU. That 0.1587 AMU is the difference between the nucleon, which is basically our protons and neutrons mass, and the mass of the actual isotope itself. This is basically the mass that will be converted into energy in this process, or sort of released as energy in this process in this case. And we could figure out that energy one of two ways. We could use Einstein's equation, which is mc squared. M here would be the mass defect. So the mass defect here in Einstein's equation is m, and c would obviously be our speed of light. So if we do that, 0.1587 AMU times our 3.0 times 10 to the 8 meters per second squared. And if we do that, we will end up with 1.428 times 10 to the 16. Now my units here are AMU times meters squared divided by seconds squared. And that is not a that is not a joule, obviously, in that particular case. What is a joule? You might remember this relationship, that a joule is a kilogram meter squared second squared. So we're very close here. We have meter squared second squared on top, but we have AMU. So we could do a conversion where we take our 1.428 times 10 to the 16 AMU meter squared second squared. And we could divide it by this number, which might look familiar to you, 6.022 times 10 to the 26, not 23, but actually 26 AMU in a kilogram. Avogadro's number is 23, and that is in a gram. 26 is in a kilogram. So that's where that number comes from. So it's basically Avogadro's number, to the 26, which will get you, again, not to grams per mole, where you kind of think about Avogadro's number, but actually kilograms. What that will do is cancel out my AMU, and that will leave me with 1.428 to the 16 divided by 6.022 to the 26 gives me 2.37 times 10 to the minus 11. Units would now be kilograms, meter squared, second squared, and now that is a joule, and that basically is joules at this particular point. Now, oftentimes when we talk about binding energy, we oftentimes give the binding energy in joules per nucleon. So if we divide this by 19 nucleons, remember nucleons are basically the protons and the neutrons. This gives us a binding energy of 1.25 to the minus 12 as our binding energy per nucleon. Joules per nucleon. Question on that calculation. So that is, how we could calculate the binding energy per nucleon using Einstein's equation. Now, just to show you that, these two conversions over here, they're kind of based off of Einstein's equation, which means you could kind of shortcut the calculation, really. And you could sort of shortcut the calculation if you have these conversions by taking your mass defect back here and going 0.1587 AMU. One AMU is 931.5 mega electron volts. The AMU will cancel. 1 mega electron volt is 1.602 times 10 to the minus 13 joules. And if you do all those numbers there together, you will actually end up with hopefully the same number there. Our 2.37 times 10 to the minus 11. which puts you here. And then obviously you could divide it by 19 and get down to here. So you could actually use these conversions instead of sort of Einstein's equation and converting it with basically Avogadro's number as well. Both will get you to the same spots, as you can see. And again, like I said, if you at this point divided it by the 19, you would be in business in terms of the same there. So there's a couple different ways you could do this. There's also, if you wanted it in mega electron volts, obviously you could stop here and divide by the nucleon, and you'd be in mega electron volts per nucleon, which is a common unit. Or if you went this way, you could then use this conversion to go from joules to mega electron volts as well. So, it's really a preference as to which way you want to kind of calculate it. But they both will get you really to the same result, which however you want to kind of do those conversions. Any questions on those calculations there?
Professor?
Yeah.
Why did you multiply by the speed of light instead of multiplying by the value of joules of 1 AMU?
Yeah, so I was just using Einstein's equation, which is technically sort of the equation that's sort of used for this calculation, and c is the speed of light in that case, and that's why we did that. And again, those conversions on the bottom I just did, they're really kind of based off of like Einstein's equation and kind of like almost like constants that you sort of get values from it. But the true, I won't say old way, but the true way of sort of doing it is sort of using that Einstein's equation where c is obviously the speed of light. So that's why we used it there. Other questions on that? Okay, so what is nuclear binding energy? Well, nuclear binding energy really is a measure of stability, as we will talk about. And since we're out of time, we will not talk about it right now. So we will lay it up there.